Welcome to our webinar today on how and why Texas-based Helena Laboratories ensured the future of its core CAD data to avoid major product development disruption in the next 5 to 10 years. We'll also hear from a CAD development expert on what a CAD kernel is and why it's critical to anyone facing a change. So now let me introduce Billy Oliver from Beaumont, Texas-based Helena Laboratories. He's a longtime CAD user and expert in multiple systems throughout his career. He'll be followed by Dan Staples in the Solid Edge Development Group. He's our Director of Development, and he'll be talking about the experience of changing out a modeling kernel in Solid Edge back in the late 1990s, and he'll be explaining more details on exactly what the kernel is. So with that, let me hand it over to Billy.
Thank you, Mike. My name is Billy Oliver. I'm with Helena Laboratories. We are a medical diagnostics manufacturing company located in Beaumont, Texas. We basically design and manufacture clinical laboratory instrumentation, and we're the reagent manufacturer also. Our clients are major medical centers, small hospitals, large laboratories, and doctors' offices. Some of our clients are Duke University, Mayo Clinic, LabCorp, and Kaiser Permanente. Our main product lines are electrophoresis analyzers, densitometers, hemostasis reagents, other instrumentation. Our basic products are used, electrophoresis is used in HDL and LDL cholesterol testing, cardiac enzymes for detecting heart attacks and whatnot, plus a lot of other things. Our blood coag product lines, one of their uses is during surgery to monitor the heparin levels during operations. We have more than 24 patents in-house, and our product line expansion has been through internal innovation and acquisition of other companies. Our primary manufacturing center is here in Beaumont. We have about 800 employees, and we have subsidiaries and distributors worldwide. My basic CAD experience started back in 1981 at a company called NL Industries. I've always worked in 3D. The company I was working for in 1981, we were the third company in the United States to buy computer vision CADs for. I used computer vision at Schlumberger, Whirlpool, and Motorola. I used Personal Designer for a while, for about a year. I was a VAR for them for about a year. I've used SDRC Design and Master Series starting in 1990 at Motorola. I used it at Cherry Electric, Zenith Data Systems, MPC Products, Eaton Corporation, Samsung, and Navini Networks. At Motorola, we were a CV house at the time in the late 80s, but due to computer vision fighting some hospital takeovers, their software began to stagnate, and they couldn't keep up with the industry. And we did an evaluation between PTC and SDRC side by side, and our division chose SDRC. I've used PTC Pro Engineer a little bit at Motorola, Navini Networks, and Point Innovation. My SolidWorks experience started back in 1995. Co-founder of a company called Palm Products. We were looking for design tools, and we ended up purchasing SolidWorks, but it was kind of by chance. We had seen an ad for the design engineering show in Chicago coming up. There was a SolidWorks ad on one side of the page and a Solid Edge ad on the other side of the page. We spoke with both VARs, and we had planned to go talk to each one of them and to make our decision on what software package we were going to buy. But the SolidWorks VAR was on the way home. We went by there first. We looked at the software. It was a pre-release state, and he made us a deal we couldn't refuse at the time, and said he'd give us 50% off if we bought right then and there. And so we never had a chance to look at Solid Edge Live, so the sales guys got us, and that's how we really ended up with SolidWorks. We used it for Scorpion recreational products. I was a co-founder there also, And the snowmobile design was used in the SolidWorks worldwide marketing campaign. And here I've used it at SolidWorks also here at Helena Labs. Here at Helena Labs, they have CAD key, and I was exposed to that here, and now exposed to Solid Edge, since we're a new Solid Edge customer. Here at Helena Labs, basically they've been using CAD key since DOS, actually, and we have about 18 years of products designed in 3D wireframe. And currently out of the complete product line, there's about 10 products that are still on the market. And and the slide you're seeing on the screen is an example of the Spiffy 3K. It's a wireframe model on top, and on the bottom, those two smaller images are the wireframe imported into Solid Edge. The problem we had here at Helena is the products are still selling well, and we needed a path to update and modernize and stylize the existing products. Helena had been looking at a solid modeler for several years before I got here, and they had been looking at SolidWorks. They were familiar with it. Some of their vendors had it, and basically they hired me because of my SolidWorks experience, and we purchased SolidWorks here shortly after I came on. The problems we encountered with it, trying to bring our old data through, we tried in 2008 releases and 2010 releases using the feature recognizer in SolidWorks, but it just didn't work very well. The models that were created were really pretty poor representations. Really didn't create a real usable model for us. The slide you see here, this is the same 3D wireframe model. The image okay, the image you see on the top of the screen, the picture, that is on the left-hand side is the electrophoresis machine. On the right is a liquid sample handler. These two machines are used in conjunction. Okay, the next slide. Okay, this shows that wireframe model imported into Solid Edge. On the left is the machined components of the Spiffy 3K. On the right-hand side is the sheet metal parts imported into Solid Edge. And, with live rules, with Synchronous Technology, we have 100% usable data. In just a few clicks, with the sheet metal side, we create a sheet metal model, and in just a few seconds, we can, flatten the part that was drawn in wireframe, 10 years ago. The effects of the kernel change on us here at Helena became apparent in right after the SolidWorks World 2010. I was reviewing the results of SolidWorks 2010 on the web, and basically saw the presentation of SolidWorks V6, but there was really not any definition or clarity about what SolidWorks V6 really was or when it would get here. So basically, I was like everybody else. I went to the SolidWorks blogs. I was trying to figure out, like everyone else, what was going on, what was SolidWorks V6. There was talk of the cloud. There was talk of CATIA Lite. There was talk of the softification of SolidWorks, and then the talk of the solidification of the SO. And really, there was a bunch of speculation. After probably 4, 5, 6 months of that, I contacted my local VAR and asked him what's going on with the SolidWorks V6. What is it? What it's about? And he told me he couldn't tell me anything else that wasn't in the blogs. and he suggested that I call SolidWorks. And I basically called SolidWorks and asked them about it, and changing the kernel to SolidWorks V6 and all this, and they confirmed that they were changing, but he assured me that SolidWorks would have a Parasolid product for years to come. The problem with that issue is, what are we going to do? As far as the reconversion being a big negative to us is, we've already been waiting since 2010. We really don't know where V6 is going to be. We don't want to wait another year or 2 years or 3 years on V6. We don't want to spend years and all these man hours becoming experts at SolidWorks Parasolid that's going away, or going to the cloud, or going to V6. And we don't want to put all this effort into a Parasolid model that in a few years, sometime in the future, is going to be moved to a V6 kernel and have to possibly be recreated. As far as the kernel change impacting us here at Helena, I expect the change to take years, and I really believe that's what's been going on at SolidWorks for the last several years. They showed us something at the SolidWorks World 2010. They've been working on that for a while, and basically, I've been on the wrong side of kernel changes before, and I really don't want to risk going from Parasolid to the V6 kernel. As far as can't afford to wait any longer, we've already been waiting since SolidWorks World 2010, and really don't know much about what's going on now. There's been no product roadmap communicated to us. The blogs have been filled with speculation, but we really haven't had anything in writing from SolidWorks. As far as stagnation of development, I believe that's already been shown inside SolidWorks. The blogs for the last few years have been full of complaints about the lack of functionality improvements, modeling issues, and that's just been everywhere. As far as the uncertainty of future modeling capabilities, there's really been no definition about what V6 is, what it will be, and what its capabilities will be. And as far as data management concerns go, with their EPDM, we've been told that the engine underneath that is being changed to the Innovia, and really there's a lack of expansion capabilities with that product. As far as us at Helena staying with the Parasolid kernel, we're comfortable with that. It's a proven technology. We know what it is. It's not an unknown. Everybody knows the issues with the translation between CATIA V4 and CATIA V5 with Airbus 380. The wiring harness, they said, was done in V4, and the airframe was done in V5, and, it caused major problems. And as far as who's the clone and who's the real thing, well, Siemens owns the Parasolid kernel. SolidWorks has just been leasing it all these years. And like Parasolid is a known, proven commodity. And V6, it's a big question mark. As far as the Synchronous Technology dividend goes, this is where Solid Edge leaves everybody behind. The mythology of Synchronous Technology, the live rules, the steering wheel, the sheet metal modeler, nothing holds a candle to it right now. And as far as one of our co-workers, Bob Serene, he's basically what his experience in working in the SolidWorks tutorials is what prompted us to look closely at Solid Edge. He's like employee number 4 here at Helena, and he has been a major a contributor to most of the designs here over the years. And we did have classroom training in SolidWorks, and he was just going through some of the tutorials, trying to come back up to speed with SolidWorks, get familiar with it again. And he started asking me questions as he was going through the tutorials about why do I have to keep going back to the history tree to do all this work. And one of his comments was, I'm looking at this hull of a part in a solid model. He goes, why can't I just grab the hull and move it? And he goes, why can't I just window around all this stuff and stretch it? And I thought, you really can't do that with history-based modeling technology. And he basically felt like he was going backwards in his methods because in wireframe modeling, he was able to do these things. He could window stuff and stretch it. He could grab stuff on the screen and move it. And I basically had to keep telling him the methods that he was asking about were direct modeling techniques, and that SolidWorks didn't do that, and, you know, there was no science SolidWorks, you know, doing that in the future. And he said, well, let's look at direct modeling stuff. He goes, I want to see direct modeling stuff, and that really pushed us into getting the first demos on Solid Edge. So basically, using the history-based method was very frustrating to our designers because of the methods they were used to with the wireframe, ease of stretching the parts and moving stuff around. And basically, ever since SolidWorks World 2010 happened, we have been trying to figure out what was going on with SolidWorks, and we never quite figured it out. And when we finally saw Solid Edge, we had a demonstration with Solid Edge, we decided to purchase Solid Edge. We had a meeting, and then everybody said yes. And I finally, for the first time in like 18 months, knew for certain what our path was going to be, because I've been trying to figure it out ever since SolidWorks World 2010 and never really could. So I had a good, calm feeling and a feeling of certainty of where we were going to be a year from now, and it was a good feeling. And the picture on this slide here is a product that was designed in SolidWorks that transferred, you know, completely into Solid Edge. So Solid Edge at Helena, we achieve 100% conversion of the SolidWorks data into Solid Edge. We're using the technology today. You know, we bypassed this multi-year transition of SolidWorks to V6 with all the uncertainty. We don't have to waste any more time and effort using a product that's going through a transition. The next several years that we'll be using Solid Edge will be all valuable to us 3 years from now, because we don't have to change anymore. With Solid Edge Synchronous Technology, we're going to be able to cut our design and edit time down tremendously. In Synchronous Tech, with the live rules, the interrelationship of the parts and the assembly, now Bob can window those parts he sees on the screen and stretch them and pull them. The whole history-based process, the method is now gone. You know, and everybody knows that history-based modeling sometimes can be very tedious, especially very complex models, very large models, and with the regeneration problems and models blowing up. We'll now be able to salvage all this existing data that we have in our product line, the wireframe modeler, and we can import any vendor data, step, IDIS, whatever, and it's no longer a dumb solid like it was in SolidWorks. The Synchronous Technology dividend, I would suggest for those of you who haven't seen Synchronous Technology and Lab Rules, I would say go to the internet and look at some demo videos. This is a comment here from Matt Lombard. He's a big SolidWorks blogger. I followed his blog for years, and he posted this just the other day, and I agree with everything he's saying here. The Solid Edge right now, it is the best product out there for machine design, sheet metal models, drawings, live rules, the steering wheel, the inter-part relationships and building assemblies. And it's proven, just like what he says, it's now in its fourth release. It's parasolid. It's a tested method. Importing geometry, there's nothing that holds a candle to it. And I agree with the statement that he has here. Right now, there's no comparison to it at all. And that's why we switched. And that's all I have. Mike?
Great. Thanks, Billy, very much. And just as a reminder, there's a PDF case study on Helena Labs that you can download from the left side of your screen there if you want to read some more details. At this point, I'd like to hand it over to Dan Staples, the Director of Solid Edge Development, and he'll talk about what the kernel is, why it's important, and some other technical details, and we'll have a couple of demos in there as well on Synchronous Technology. Dan?
Super. Thanks, Mike, and thanks, Billy, for joining us today. It was pretty compelling stuff. Well, first of all, what I want to share with you today, of course, Solid Edge underwent a kernel change back in 1996, a long time ago, so we've actually done this before and know what it takes and what's under the covers. And I'm not going to personally speculate on exactly what SolidWorks is up to. I think it's best if you find out for yourself. I'm not sure it's all clear in the press. I mean, give them a ring and find out what's going on. What I'd like to do, though, is explain, what the heck is a kernel and why is it important. And one of the things I want you to really understand is it's not transparent and will not be transparent to users if there is a kernel change. There's that saying that, how do you know if a lawyer's lying? His lips are moving. I think if anybody tells you that a kernel change is, it's pretty easy and it's transparent and it shouldn't cause much problem for you, you got to listen very carefully to what they say next because it may not be exactly accurate. The fact is, there's not a great analogy for it, but some of these aren't too bad. It's not like taking a V8 engine and swapping it for another very similar V8 engine. It's really a very significant undertaking in terms of the matchup. The probably can't swap a V8 with a V4. You got a lot of things that interconnect there to other systems, and they have to work in certain ways. Same thing with a variety of other things. So I'm an engineer myself, and I know all the folks on this call are engineers, and so I think you want to probably look under the hood and understand, well, okay, so I got Billy's story. I understand it. It's pretty compelling, but what exactly is this kernel, and what does it mean to me? So I want to explain a little bit of that to you because I think you want to just have some good understanding of this as you make your decisions going forward. So let's start with probably the least controversial piece of this puzzle, and that's two pieces of the heart of the CAD system are the 2D sketcher and the 3D assembly solver. So the 2D sketcher, this isn't the perfect picture for it. This is a schematic, but you make sketches in 2D, you put dimensions on them, you edit the dimension values, and they update. Well, that's actually not done by, generally speaking, the CAD vendor, by SolidWorks or Dassault or whomever. That's done by a third party that supplies technology to them, and we'll talk about that more in just a second. So that's the first kind of kernel-y piece, is this constraint solver that does the solving of the profiles or sketches or whatever you want to call those. Another piece of technology is the thing that does the solving of assembly part locations. So, you put together parts, you mate, you align, you insert, you do all those kind of things, and it's basically solving the locations of the parts in some sort of simultaneous way. And again, that's not something the CAD vendor generally writes. It's a particularly complicated and interesting piece of math, and it's typically supplied to the CAD vendor. Now, these two actually end up being the least controversial part of this discussion, as we'll see in just a second. Now, the other thing, and I think a lot of people don't realize this, is a very large percentage of what you do in SolidWorks or any other system is, again, the core math that's doing all that is not coming from the CAD vendor. It's coming from the underlying geometry kernel. So when we say geometry kernel, this is what we're talking about. When you do a solid, you extrude a solid, you cut away a solid, you sweep a solid. All these kind of things are generally done by math that's down in this thing called the kernel. And I guess we call it a kernel because it's kind of like the innermost workings of the system, if you will. Surfacing, a lot of that comes from the kernel. Some CAD vendors do add extra surfacing to their software. All of the blending, and maybe that's not a good term that you guys would use, maybe rounding or fillets or whatever you want to call it, that's generally all coming from the kernel as well. So when you're in SolidWorks and you say, I want to round these three edges, and you get a result, what's happened there is they've made a call to the Parasolid geometry kernel. It's computed that result and given it back to them, and then they put it on the screen for you. Same thing with shelling, or what in SolidEdge we call thin wall, but shelling out a part, all done by the kernel. Interference checking, mass properties, all these kind of things are actually done by this kernel. Now, and this is really the core of it and where it's going to get particularly relevant to you, I think. Now, there's other pieces that, interestingly enough, are generally done by the kernel as well. Being able to select things, bore line intersection, I guess that's kind of a geeky software development term, but basically when you click on the screen, finding all the stuff that's under your cursor, often that's done by the kernel. And then usually the display as well. So computer graphics cards, whether you have an NVIDIA or an ATI or whatever, they don't understand anything but triangles. They can't display B-spline surfaces. They can't display cylinders. They can't display spheres. They display triangles. So what the CAD system does is it takes whatever it's got, in this case, some B-spline surfaces representing the casing and the rounds and so on. It breaks those down into a triangle mesh. You personally, as the CAD user, never see that, but it breaks it down into a triangle mesh, and then using some shading averaging techniques, it sends that triangle mesh to the video card, which actually does the shading averaging. That makes it then appear like a continuous solid. And so that typically that technology called tessellation is also provided by the kernel. And then the final piece that's provided by the kernel is the drawing creation. So, you want to put your parts and assemblies on the drawing, and it needs to properly hidden line everything. This is a very specialized, very hard piece of math to get all that right and do it all very quickly. And it's really been one of those things that CAD systems have wrestled with over time. I can share with you the fact that back in the early or mid 90s, when we were ASIS based in SolidEdge from 96 to 98, we struggled with hidden line calculation using the ASIS kernel, and it was not fast enough, and it made mistakes. And when we moved to the Parasolid kernel, it got an order of magnitude faster, and it didn't make mistakes. So the point is that this type of thing can vary between kernels, and it is your life's blood. We all enjoy modeling. We're all engineers. We like to model. We like to engineer the parts. When it comes down to it, I would say a good 98 to 100% of us need to produce drawings. And producing those drawings depends on the kernel to create the correct representation for the part in the final analysis. So I wanted to share these things with you because, you probably hear these things thrown around the kernel. What is a kernel? It's the underlying geometry, rounding, solid operations. It's the hidden line. It's often a lot of the display system as well. So who supplies these kernels to whom? So I think a really interesting point that also a lot of folks don't know is that Siemens, us, the folks you're talking to on the phone today, supply the kernel for a lot of key operations in SolidWorks and quite a few key operations in CATIA as well. So that 2D solver that I spoke of, when you create a sketch and edit a parameter value or a dimension and it changes the sketch, that technology is supplied by Siemens to both SolidWorks and to CATIA. And, of course, to SolidEdge as well. Same thing for the 3D assembly solver that does the assembly solving, also supplied by Siemens ourselves. Now, these two lines are the least controversial in that I certainly haven't heard any rumblings or anything in the press or blogs or anywhere else that said, hey, either Dassault or SolidWorks are thinking of swapping out the 2D solver or the 3D solver. So I know of nothing to lead me to believe those are changing. So most of the discussion is on this final line, and again, I invite you to get the true story from Dassault, not from anybody else, really. But right now, SolidWorks uses the Siemens kernel Parasolid, SolidEdge uses Siemens kernel Parasolid, and Dassault uses their own proprietary kernel. And that's what the speculation and discussion. It's really not, speculation per se, and that there was certainly some announcements at SolidWorks World 2010 that Billy alluded to that started this whole discussion. So anyhow, the point is, what will the kernel be in that SolidWorks box in coming years, and how might that affect you? So let's going back to the kernel itself for a second. I think I showed you some pictures, and you're all familiar with this. You use solid modeling day to day. You do your sketches, you solve them, and then comes some solids are constructed, and then comes the display. Well, I think the thing that a lot of people forget or don't realize is that when you edit in the history tree, it's really editing's almost a misnomer. What it does is it rolls back, it undoes everything up to the point of the edit, and then it completely redoes that in order to achieve its goal. And so what that means is that every time you edit a feature, you are completely reconstructing from scratch every feature that is downstream of that. And so this middle box where the solids are constructed and the Boolean operations happen and all that is really, really important. And what's really important about it is that it needs to be exactly the same every time in order to get the same solid out the back end. And what I mean by that is that, when you construct a solid, you build your next feature and you dimension to one of the edges of the solid, or you include an edge from one of the prior features. Well, all of that everything that precedes you has to come out exactly the same in order for everything that comes after to work properly. So much so that, in fact, and I'm sure SolidWorks does this also, we version our algorithms. So if we were to improve an algorithm on how you do a round on, a certain situation, then we would, in fact, version that so that your existing files would always use the old math to compute it, so you can be guaranteed to get the same solid at the back end. If we were to use the new math, there's no guarantee that you'll get the same solid out the bottom of the tree. And that's the point about kernels. Not only is it's not like we're just changing the math a little bit. You're really changing completely from one set of mathematics to a completely different set of mathematics. And unless every answer is exactly the same in every feature, in every tree, in your models, you will not always get the same thing out the bottom end. So I want you to understand that as engineers, and as I say, talk to other folks about what exactly is happening, but understand how important the kernel is and what it's really doing. So just to give a little bit more of a point on this, and then I'll show you a couple of videos that I think you might find of interest. We talked about how the kernel's doing the Boolean operations, the cutting and the adding and so on. It's doing the rounding, or sometimes that's called blending. A lot of the surfacing comes from the kernel. Also, don't be fooled by the fact that performance is a big part coming from the kernel, and reliability as well. So as I said, when we changed from ACES to Parasolid, and believe me, that was no mean feat, and our customers, frankly, were not very happy with us at that time. It was, it affected, in our case, we were moving to a better kernel. Performance got faster and more reliable, and that was a great thing. But we did have certainly a lot of issues with the history tree and getting the same result at the bottom of the tree, and it's just factual that that's going to occur. Now, just to give you a little example of what I mean by the differences. Now, this is maybe not the example you're going to run into every day, but I think it's important to understand. So on the left-hand side, I have a 4-edge round done in SolidEdge and SolidWorks. They use the Parasolid kernel. They will produce the exact same result. I have Inventor on the right, and the only reason I picked Inventor is it uses a different kernel called Shape Manager. And what you see here is that they actually produce quite different results, right? So, if you look at it, first thing, obvious thing is, there's multiple patches produced on the left and a single patch on the right. And you can argue whether one of those is better or worse, and some will like one and some will like the other. The point is they're different. And if you compute this 4-edge round in different kernels, you will get different answers. You can see in the Inventor they do this thing we call a suitcase corner by default, where that little arrow is pointing. That's kind of got a little built-in round there. whereas the SolidWorks Solid Edge answer doesn't. And there's an option to do suitcase corners, but the point is the answer is different out of the box between the two. There's different edge count, which matters a lot to computing downstream features. So, again, why is this important to you? I think the thing you want to think about is, okay, so in the future what, right? SolidWorks 2012 will today produce exactly the result you see on the screen here. Solid Edge will produce exactly that same result. So what you've come to rely on and say, well, SolidWorks does this for me, does that for me, produces this result that I like, what you're really saying is the Parasolid produces that result, and therefore Solid Edge will produce that exact same result. And, dig into it and see what is it that V6 will produce and how might you be impacted. So, and that's really all I ask of you. Obviously I would certainly like the business of every person on this phone, but I also want people to be successful, and I want you to choose whatever obviously is the best for you. I'm also interested in the CAD industry, doing well, being known as people of high integrity and so on. I think it hasn't been clear exactly what's going on with Dassault and SolidWorks, and I would love if they would just write up and make it clear. But if not, I'd say go, dig into it, ask them yourself, find out exactly what's going on and figure out how it's going to affect you. And or take a look at what other alternatives exist. In general, with Solid Edge, all I ask is that you give us a fair shake and look at what we have to offer. People who do, like Billy, generally find, hey, maybe I didn't look at it because it wasn't the most popular, but holy cow, now I'm really glad I did because it's providing me a lot better functionality and I'm able to do my job more quickly. So you're both, ensuring that investment in sort of your Parasolid and keeping that proven functionality, reliability, and performance. And at the same time, if looking at Solid Edge, you got to realize you do have the best of both worlds. If you want to be a completely history-based person, Solid Edge has complete history-based, setup just like SolidWorks does. If you want to take advantage of Synchronous Technology and what it brings to the table, then there really is no comparison, as Billy said. So in that respect, what I'd like to do is take you through a couple videos because I do want you to be able to see a little bit of what we're talking about when we say, well, the additional benefit of Solid Edge is in performance around Synchronous Technology. What does that mean? And so with this particular video, we'll take you through, and it's going to be narrated online. You'll hear it. I'm going to not be speaking for a little bit while it does its thing. But it'll take you through editing the same part using a history-based technique, and we're using Solid Edge because it has a full history capability, and taking that same set of edits through using Synchronous. And so look and compare and contrast those two is what this is about. And with that, we'll go to the video.
If you've used a traditional 3D CAD system, you're familiar with performance issues due to model regenerations. Let's look at a typical engineering change order scenario and see how much faster edits can be made using Solid Edge with Synchronous Technology. Most change orders begin with documenting a set of requirements. View and Markup in Solid Edge allows you to efficiently mark up assemblies, parts, and drawings, which can be emailed using a lightweight PCF file. Recipients of the file can view the changes in Express Review, a free viewer that can be downloaded today. You can package all types of documents such as requirements documents, spreadsheets, drawings, and even images. After reviewing the requirements in this engineering change order, it's time to make the edits. Before we show you just how fast Solid Edge with Synchronous Technology is, let's refresh your memory on what it takes to make changes in a traditional 3D CAD system. We'll start with this console cutout. Feature edits in a traditional CAD entail a delete and recreate process, so during any edit, the model rolls back, deleting all subsequent features. Only features built to accommodate future changes will update correctly. We got lucky here as this feature was constrained to keep the cutout in the correct position. This simple edit took over 15 seconds to make, but larger models can take much longer. We'll make similar edits to the frame and hanger clearance pockets. Once the edit is complete, all remaining features must regenerate, even operations that were not affected by the change. This rebuild process is a common source for model failures because subtle changes can cause severe and unexpected results. The behavior of this 20-year-old architecture is what most people consider the norm. Let's now make a more complex edit to the tank profile. Since this change wasn't something the designer planned for, the results will be unpredictable. Once the edit is complete, notice how many features failed. The original designer didn't build the model in anticipation of such a change, and this is a classic problem found with traditional CAD technology. During the regeneration process, subsequent features are bound to break. Imagine the number of steps required to fix all these features. Creating models flexible to changes in a history-based system takes a tremendous amount of pre-planning during the construction phase so that edits will give the correct results. As we see here, the model wasn't built to accommodate even the simplest changes, and if you did not originally create the part, you have to untangle someone else's mess before you start. Let's now see how SolidEdge with Synchronous Technology eliminates these issues. We'll make the same changes in SolidEdge so comparisons between the technologies can be seen. An initial difference is how models are edited directly. With this approach, changes are made directly to the geometry so you can edit in the most convenient way. Simply drag a face or add 3D driving dimensions. Remember, the edits with traditional CAD took a while to recalculate and lots of additional time was required to fix failed features. But using SolidEdge with Synchronous Technology, these edits are done in just a few seconds. The edits you see here are happening in real time. When you need to make fast, reliable changes, there really is no better system than SolidEdge with Synchronous Technology, even with parts coming from other systems.
Okay, so hopefully that video gave you some feel for, the difference between doing a history-based kind of playback, if you will, and being able to do things directly in synchronous technology. And obviously there you see what we mean by performance. But again, you've got to put in your mind as well the fact that that replay of features is just what I was talking about earlier. In a different kernel, it's not going to necessarily replay exactly the same, and the results won't necessarily be the same. But right now, let's just focus on that performance aspect, which I think is really bringing people like Billy a lot of value to what they can do. Now, the next video, I think, is really interesting, and it shows the same thing several times, but I think it's important actually that it does because it's something you've probably never seen before. You're probably sitting there going, okay, well, this is all great, but what do? I got a bunch of SolidWorks files. I got a bunch of SolidWorks drawings. How can I really reuse those in SolidEdge? And what you're going to see, now I know it's, it's voiced over, so it's going to explain it, but get this in your head first because it is kind of surprising. You're going to see us take a SolidWorks model and bring that into SolidEdge. We can open SolidWorks models directly. And then what we're going to do is take the drawing of that same part, and we're going to use the drawing of the part to inject the dimensions off of the drawing onto the part itself, and then use those dimensions to edit the part. So, again, you're going to see actually the solid model and the drawing sort of merged, if you will, where the manufacturing dimensions off the drawing are pushed into the solid model, and then the solid model is edited with them. And with that, I'll let the video speak for itself.
In this demonstration, I'm going to be showing you how SolidEdge preserves 3D intent from imported 2D drawings to imported 3D models. In this particular case, we're going to be looking at a couple of files from SolidWorks. We have a SolidWorks part file and its associated drawing. So the first thing I want to do is get the part into SolidEdge. So I'm going to import that into a SolidEdge part file. Then I'm going to go ahead and save that. Then I'm going to open up the associated drawing file. And we can look at the translation wizard. You can see that we get a preview. We can see all the layers that are involved. You can map all of the different aspects, such as the line type to a SolidEdge line type, and line colors to line widths. Once we have that in a SolidEdge draft file, we want to make note of a couple things. For instance, the drawing scale. You can see that the scale is set to 1 to 5. There's also a detail view that is 2 to 5. And that'll become important later as we go through this process. Now keep in mind I'm showing you this on a couple of SolidWorks files. This would work on any imported geometry such as something from ProEngineer, Mechanical Desktop, or Ideas. just to name a few. So I'm going to turn off the GD&T and the border layer so that we're just looking at geometry and dimensions. And what I'm going to do is run the create 3D command. What this is going to do is allow me to associate this 2D geometry to a 3D model, in this case the imported model. We want to make sure our options are set to include dimensions. We want to take along the linear, radial, and angular dimensions. And then we also want to define the scale, which is set correctly here. It's 0.2, which is 1 to 5. The front view is the primary orientation. So we can just begin selecting views. And we also want to make sure to get the top view and add those to the geometry. So you can see what happened. It took the 2D sketch geometry and it applied it to the 3D model in the correct orientation. So if we look at the different views, you can see the sketch lines up with our 3D model. So right now those dimensions are only associated to the sketch, but what we want to do is associate those manufacturing dimensions to the 3D model. So we have some user-defined sets here. The last one is a collection of all of them. I'm going to turn those off, and I want to do these one at a time. So if I want to associate the dimensions to the model, I can just right-click and attach PMI, and you can see that those dimensions actually jumped from the sketch directly onto the 3D geometry. And now those manufacturing dimensions become driving dimensions of the 3D. Another important thing about Solid Edge when you're importing files is we can maintain design intent on the imported file. Traditionally, when you're importing geometry into a foreign CAD system, you'll lose the design intent. So for instance, what I'm talking about is we have a couple of holes there that are aligned along the z-axis. If I edit this dimension, which is only associated to the bottom hole, and begin to manipulate that dimension, you can see that it maintains that alignment along the z-axis. If you look down here in the live rules, you can see that it turned green along the z-axis, which means it found that relationship and it's maintaining it for us as part of the design intent. We don't have to worry about it. So we change that to whatever we want and it will maintain that alignment. Let's go to the next view. And we want to also attach that geometry, or that PMI, to the geometry. Again, if I modify this dimension, if I make this taller, you can see that design intent is being maintained, that both sides are adjusting based on a live rule that says that those two are symmetric or coplanar. I also want to attach the PMI from the top view. See how it moved down, migrated to the 3D geometry. And once again, I can take advantage of these dimensions. I may want to lock this dimension. I always want this to be 25.4 millimeters wide. If I modify this dimension, watch what happens. You can see that the rib on all four sides, or all four corners there, is moving. And again, that's design intent. I want that to remain symmetric all the way around. And it does that for us automatically using those live rules. Okay, notice we have some holes along the side. We don't have any PMI dimensions attached to that yet. If we go back to our drawing, you can see that we actually had an auxiliary view. So I want to add that into our model. Scale's the same. Just run the command again and it brings it in there. Now what I want to do is actually manipulate that to get it in the correct orientation because it brings it in relative to its origin. Rotate it 90 degrees. Then I need to change the orientation of the steering wheel because what I want to do is put that steering wheel centered on a hole and then use that to align to a hole in our model. I'm going to go ahead and move this up just so you can see that it does in fact line up on that edge. And at this point then you can just right click and attach the PMI. Now that that PMI is attached, again, that becomes driving dimensions. And then finally, I had a detail view, an enlarged detail view of this particular area up here at the top. So again, I'll switch windows back to the drawing. And here's our enlarged view. Remember, this was a different scale. So this time when we run Create 3D, we need to set our scale to twice that, to 0.4. And just select that geometry and add it to the model. Again, we'll reorient the steering wheel and reposition it. Make sure it's on the end. And then I'm going to move it in plane up to this endpoint. And then I'm going to attach the PMI dimensions to the model. So once we have that all done, you can see that now we have all the manufacturing dimensions have now been attached to the 3D model. And it becomes a fully synchronous solid edge model at this point with all those manufacturing dimensions. I'm going to save this, and what I want to do now is actually create a drawing from this. So I'm just going to go to the Create Drawing command. And now what we'll do is just, I'm going to move these views around just a little bit. And then I'm going to retrieve that PMI dimensions onto this drawing. So just run the Retrieve Dimension command, select the views, and it retrieves all the dimensions associated with each particular view. So you can see the dimensions that we changed are all correct. So you can see how powerful Solid Edge is for importing geometry from foreign CAD systems, 3D geometry, and the associated drawing file with all the manufacturing dimensions, and then actually attaching those manufacturing dimensions to the 3D model and making it a fully synchronous Solid Edge model.